Today we are going to discuss some of the examples of scattering problems. So the first one is the scattering by a hard sphere. So what we consider here is a hard sphere of radius a as shown here, and the potential of this sphere is represented like this. It is 0 outside this spherical surface. That means when your r is greater than this radius of the sphere, you have 0 potential, and we assume an infinite potential for all points within that sphere for r less than a. And this potential represents an impenetrable wall, and it mimics the classical image of scattering. Now, because of the infinite potential within the radius a, Born approximation cannot be used here, so we have to consider the partial wave analysis to solve this problem. Now we do it for two different energy ranges. In first case, we consider low energy of the incoming particles. So that means it has a momentum k which is far less than 1 by a, or ka far less than 1. Then the potential barrier inhibits the particle from entering the region of the scatterer, and you can show that within this low energy limit the scattering occurs only for L is equal to 0 partial wave. So in the partial wave analysis, we need to consider only the S wave contribution for low energy limits. Now if you consider the radial part of the Schrodinger equation that we have seen during the development of partial wave analysis, we had an equation something like 2m by h rho square into V of r minus d square by dr square minus k square r rkl is equal to 0. Now for this particular problem, for the low energy case, then you can see that the potential is 0 just outside this sphere. So you can take this term is 0 just outside the sphere, and you can write it as minus d square by dr square plus k square r rkl is equal to 0. Now let's make some substitution. We put, instead of r into capital R, we put another variable u. Then you can write this equation as d square u of r by dr square plus k square u of r is equal to 0, where this k square is basically given by 2me by h rho square. Now this is a simple second order differential equation. So you know the solution to this equation, and this is the solution is given by u of r. We can consider two cases. We can take it as u1 of r is equal to 0 for r less than a, and for r greater than a we can write it as u2 of r, which will be a sin kr plus delta 0 for r greater than a. So we have obtained two solutions for two different values of this distance or the radius vector, position vector, u1 for r less than a and u2 for r greater than a. Now we have introduced a phase shift time delta 0 as we have seen in the partial wave analysis, and this will tell you that the degree to which the scattered wave function differs from the spherical Bessel function, or you can say that the degree to which the scattered wave function differs from the incident waves. Now we have a boundary at r is equal to a, because that is the boundary of the scattering potential, and if you apply the boundary condition for these wave functions, you can say that at r is equal to a, or u1 of A must be same as u2 of A. It has to satisfy the boundary conditions. So this has to be 0, because u1 of R at R is equal to A must be 0 as given by this expression. Okay, so it tells you that you can write sine Ka plus delta 0, or A sine Ka plus delta 0 must be 0, or this is 0 when the sine term is 0, right? Or you can say that the argument of the sine Ka plus delta 0 must be of the order of n pi, where n is equal to 0, 1, 2, 3, etc. Because for all these values of n pi's, the sine term goes to 0. So you get some expression for the phase shift delta 0, and this is given by n pi minus Ka. So the phase shift we have specifically written as delta 0 because we are considering only L is equal to 0 case, S partial wave scattering on alone. That's what we have written delta as delta 0. Okay, so the minimum phase shift you can write as the minimum phase shift delta 0 equal to minus Ka, because n is equal to 0 is the minimum value that n can have. So this is given by the minimum phase shift is given by minus Ka, and this is usually negative for repulsive potentials. So you can write the total scattering cross section, total scattering cross section sigma is equal to 4 pi by K square. Sigma L is equal to 0 to infinity 2L plus 1 sine square delta L. Now for L is equal to 0 case, for this particular case we can write the total scattering cross section as sigma 0 is given by 4 pi by K square sine square delta 0. So this is, if we substitute the value for delta 0, this will be 4 pi by K square sine square Ka. So for very low energies we have this quantity Ka, which is far less than 1. So you can write this sine Ka for very low energy, this is approximately equal to Ka. So the scattering cross section can be written as 4 pi by K square, then we have K square A square. So this is equal to 4 pi A square. So this is the scattering cross section in the low energy limit. And if calculate this scattering for using the classical mechanics, what we get is pi A square. So compared to the value that we obtained from the classical mechanics, we have seen that the quantum mechanics tells you that it is 4 times the classical value of the scattering cross section. And now we now we consider the other energy limit, that means in the high energy limit, or we assume that the incident particles are having very high energy such that this Ka is far greater than 1. Then the number of partial waves contributing to the scattering will become very large. Unlike the case of low energy case where we have considered only the S wave analysis, here we have to consider contributions made by many number of partial waves. So we make an assumption that in the expression for the scattering cross section we have some summation which goes from 0 to infinity. We cannot do it up to infinity, so we have to limit it somewhere. So the maximum value of L in this case we limit at, or we assume that this maximum value of L will be of the order of Ka, the energy itself. Then the scattering cross section, total scattering cross section can be written as 4 pi by k square sigma L is equal to 0 to some maximum value 2L plus 1 sine square delta L. Now since so many values of L contribute in this relation, we can replace this sine square function by its average value, and the average value of the sine square function, as you know, is half. So you can read it as 4 pi by k square into half. Then we consider the summation from L is equal to 0 to the maximum value to L plus 1. So this will give us 2 pi by k square. Then this summation term will give us L maximum plus 1 the whole square. So since this quantity is a big number compared to this one, we can neglect this one in this expansion. So this can be written as 2 pi by k square L maximum square, or if you substitute the maximum value of L, we can see that this is 2 pi by k square, and we assume that the maximum value of L can be of the order of Ka, or of the order of energy itself. So this will give us 2 pi a square. So this is this expression for the total scattering cross section if the incident particles are having very high energy. So if you compare this value with the expression that we get using the classical mechanics, this is twice the classical value for high energy limit. Next we consider the scattering by a square well potential. The nature of the square well potential is shown here. We have a potential well with the depth given by minus of V0, the potential value, and the width is given by A. So it is from 0 to A, and the potential is 0 in the other regions of this potential well. So the potential can be well represented by this term. This is minus V0 for R in between 0 and A, and it is 0 outside that range. So for this particular example also we consider the partial wave analysis, because Born approximation cannot be used for sufficiently large potentials like this one. So we consider the S wave scattering here. That means we assume that the energy of the particle is usually less than 1. So similar to the previous problem, for L is equal to 0, the radial part of the Schrodinger equation, we can write d square by dr square. So we designate two regions here. We take the wave function in this potential well region as u1, and outside this region we take it as u2. So we can write the radial part of the Schrodinger equation as d square by dr square u1 of r plus k1 square u1 of r is equal to 0 for 0 greater than r, for 0 less than r less than a, within that limit. And you can also write d square by dr square of u2 of r plus k2 square u2 r is equal to 0 for r greater than a, where the k1 is given by 2m by h cross square e plus v0. So k1 is the wave vector in this region, in the potential well region, where we have minus v0 for the potential value. So this will become k1 will become or k1 square will become 2m by h cross square e plus v0, and k2 is the wave vector that we assume in this region, that is for after the scattering process. So K2 can be written as, or K2 is given by, there is no potential energy, so this is simply 2me by h cross square. And what we assume here is that we are assuming the low energy case, and the contributions from S wave alone is considered. So the solution to these equations can be written as u1 of r is equal to a sine k1r, and for u2 of r is written as another constant b sine k2 of r. Then we have to add a phase shift term, because this potential will introduce some phase change in the outgoing wave compared to the incident wave. So in the region 2 we have to add a phase shift term delta 0. Now the continuity of the wave function and its derivative at the boundary. So what is the boundary? The boundary is r is equal to a. At this boundary, let's consider the continuity of the wave functions. Then it will tell you that a sine k1a is equal to b sine k2a plus delta 0. So if you solve this expression, you can get an expression for the phase shift delta 0, that you can do as an exercise. Solve this one and get an expression for delta 0. That will give us tan inverse k2 by k1 tan k1a minus k2a. So once you know the expression for the phase shift, we can write the expression for the total scattering cross section. So in this particular case, this is sigma 0. So this is approximately given by 4 pi by k2 square for r greater than a sine square delta 0. So putting the value of delta 0, you can write it as 4 pi by k2 square into 1 plus 1 by tan square delta 0 inverse. So this is the expression for the scattering cross section for S wave scattering. Now you can see that we have an expression for delta 0 here, or for tan delta 0. If you take this tan to the left side, we have tan delta 0 is equal to k2 by k1 tan k1a minus k2a. So under some special cases, these tan delta 0 can goes to 0. So if this tan delta 0 goes to 0, then you can see that this delta 0 goes to 0. That means there is no phase shift or phase change introduced by the scattering potential. That means the square well potential will not have any effect on a particle which is moving through that region. So this is something like what we have, you can consider it as some electrons which is scattered by some potential well in a material. So under certain special cases, not always, under certain special cases, we can have this situation where this delta 0 is equal to 0, or no phase shift introduced by the scattering potential. So in that cases, even though there exists a scattering potential, it will not affect the movement of the charged particle or the electrons through the material. So even though this is valid for a square potential well, similar vanishing of the scattering cross section would occur for localized attractive potentials. This effect was first observed by Ramsar, and hence it is known as the Ramsar effect. So he found that for very low energies of the order of 0.7 electron volt or less, the scattering cross section of electrons by noble atoms was extremely small. The scattering of electrons by noble atoms was extremely small. Third example that we are going to consider for scattering case is the Coulomb potential scattering. So we have two particles, one particle with charge Z2e here, and this is our target particle, and there is a projectile particle of having charge Z1e, which is going to get interacted by the potential of these two things and scattered by one another. So we are going to analyze what happens in this scattering example, or the Coulomb potential scattering. So the potential is given by this expression Z1 Z2 e square by R, where this Z1e is the charge of the projectile and Z2e is the charge of the target particle respectively, as I told you. Now we are going to use the Born approximation to solve this problem. Then the differential scattering cross section in Born approximation is given by d sigma by d omega is equal to 4 mu square by h cross square q square. Then we have the modulus square of integral 0 to infinity r prime v of r prime sin q r prime dr prime. So this is what we have seen in previous class. So for this particular case, if we substitute for the potentials, then we can write it as for Z1 square Z2 square e raised to 4 mu square divided by h cross square q square, where this mu is the reduced mass of these two systems. Then this r prime will go away by a 1 by r time from this potential. So in the integral, what we have is from 0 to infinity, simply sin q r prime dr prime, then the modulus square. Now let's consider this integral term. So let's say the integral 0 to infinity sin qr dr. So this can be written as the limit, let's say some limit lambda goes to 0, integral 0 to infinity e raised to minus lambda r sin qr dr. This is again limit lambda goes to 0, integral 0 to infinity e raised to minus lambda r. Then the sin qr term can be written as e raised to iqr minus e raised to minus iqr divided by 2i dr. So this is 1 by 2i can be taken outside. So 1 by 2i limit lambda goes to 0, integral 0 to infinity. Now you can split it into two integrals. In one case, integral 0 to infinity e raised to minus of lambda minus iq into r dr minus again integral 0 to infinity e raised to minus of lambda plus iq into r dr. Now you can see that these kinds of integrals, so this is what you have seen or you have studied in Laplace transforms. So what we did is basically we converted this integral into the Laplace transform form. Then we can quickly get the solution, or we can take the solutions of Laplace integrals in Laplace transform. So as you know, this will give us 1 by lambda minus iq, and this integral will give us 1 by lambda plus iq. So those are the standard results that we can take from the Laplace transform. So This can be written as, this will be 1 by 2i limit lambda goes to 0. Then from the first integral we have 1 by lambda minus iq minus, from the second one we have 1 by lambda plus iq. So this is 1 by 2i limit lambda goes to 0. If you simplify it further, we have lambda plus iq minus lambda plus iq divided by, in the denominator you can take lambda minus iq into lambda plus iq. This is equal to 1 by 2i limit lambda goes to 0. Upon simplification you get 2iq in the numerator, and the denominator will be a minus b into a plus b, which is a square minus b square. So this, in this particular case, this will be lambda square plus q square. So this is limit lambda goes to 0. The I and I can be, or 2i can be cancelled from both cases. Then what we have is q divided by lambda square plus q square. Now in the limit, when lambda goes to 0, this is simply 1 by q. So if you put it back in this expression here in this integral, so we have seen some solution for the integral part, and we will be having the remaining part. So you can write the differential scattering cross section d sigma by d omega. This is equal to 2 times z1 mu z2 e square divided by h cross square q square whole square, because the modulus square of integral sine qr dr will simply give us 1 by q square. Now you can see that q, if you remember, it was given by 2k sine theta by 2, right? And what was k? K or k square was 2 mu e by h cross square. Okay, so we can write this differential scattering cross section as d sigma by d omega can be written as 2 z1 z2 mu e square by h cross square into 4k square sine square theta by 2 whole square. So if you substitute for k square, this will become 2 z1 z2 mu e square divided by 4 into, then we have 2 mu e sine square theta by 2 whole square, because you can write h cross square k square, this term h cross square k square in the denominator can be written as simply 2 times mu e. So this will give us z1 square z2 square e raised to 4 divided by 16 e square, then we have sine raised to minus 4 theta by 2. So this relation is known as Rutherford formula for the Coulomb cross section. So this is Rutherford formula for Coulomb cross section or the Coulomb scattering. So this is the expression what we were looking for two charged particles with charge Z1e and Z2e. When it scattered through some angle theta, the scattering cross section or the differential scattering cross section is given by the Rutherford formula, this equation.